before we talk about how to implement a priority queue, it would be important for us to understand its interface. Namely, for any implementing class, what range of methods should be implemented. So that'll be important to understand first. Let's talk about it. The first method is called the min method, and you want to connect this to the earlier discussion. Remember we said for every entry, the lower the key value is, the higher its priority is. So you should always understand the connection between the key value and the priority it denotes. So in this case, if you actually want to find an entry with the minimum key value, that means you really want to find an entry with the highest priority. So what will be the precondition to find the minimum entry? Well, in this case, you definitely should make sure the queue is actually not empty. And also, what should be returned? You should really return the entry with the lowest minimum key value, meaning that it has the highest priority to really handle. Right? So that's the first one you want to make sure. The name over here, in some way, if you're only beginning to learn about priority queue, it could be a little bit misleading because you're thinking that if that's minimum, how can that be the highest? It's actually due to our choice to say the lower the key value, the higher the priority is. You want to remember that point. The second method is just about how many entries there are in the priority queue. And this method here and the next method about whether or not the priority queue is actually empty. So these two methods are exactly identical to how we handled the ADT's stacking queue, right? You can always ask about the size and also whether or not the collection is actually empty anytime. So that's why there's no precondition. And the postcondition is also very straightforward. The next method is about inserting a new entry into the priority queue. In that case, it would be okay for the key to really create some duplicates among the existing keys, because remember, the key values in the case of priority queue are not really for searching purpose. It's only for denoting the priorities for the entries. So the precondition, the only constraint might be if you got some fixed capacity, depending on your implementation. If you decide to actually use an array to actually implement your priority queue, in that case, you may actually have some fixed size. Of course, you can also grow your array's size dynamically if you want to. That's something we also covered earlier when we talk about the queue. And the postcondition for inserting will be, of course, the entry will be added into the priority queue. However, here there's no notion about whether we add the entry into the top or to the front or to the end of the priority queue. There's no such notion about top, front, or end. All you have is more like a set of entries, and somehow you have a way to extract the entry with the minimum key value or the highest priority. The final method to support will be remove min. So this one here, it's think about the connection between min and also remove min, similar to the case between top and also pop in the case of stack, and also the front and also the queue in the case of the queue. So the minimum over here is going to return the entry without modifying the priority queue. And remove min over here is going to, number one, return the current entry with the minimum key or the highest priority, and at the same time, it's going to remove that particular entry. Of course, there might be multiple entries with the same minimum key value, but you just need to return one of them. So that'll be sufficient. Right? Just remember the verbal remark I just made. So you always want to connect the current ADT we're studying to the earlier ADTs you studied already. They do share some similarity, but they also have some differences. And for the precondition, of course, the queue cannot be empty, right? And also, what about postcondition? In that case, you're simply just going to do two things. Number one, you're going to remove the entry with the minimum key value or the highest priority, and at the same time, you want to return that particular entry. So that's something I'll leave to you for the implementation. It's rather straightforward. And knowing about the interface, now we were able to actually declare maybe in Java some interface called priority queue. That's something I can leave to your exercise. Let's now focus more at the conceptual level about the implementations that we can support to really implement the priority queue. The first implementation we want to talk about will be using linked lists. For now, let's now focus on singly linked list. And then for doubly linked list, it would be for your exercise to consider whether or not some operations can be improved for their time complexity. And there are two approaches we're going to adopt. The first one is we're going to maintain a linked list that's always sorted in a non-descending order based on the key values, of course, not the element value. Always when we say sort the entry, we typically say it's going to be sorted based on the key values. If it has to be sorted based on the element values, we'll let you know explicitly. But if that's implicit, that means the key values is really the sorting criteria. And approach number 2 is about unsorted list. And I want you to think to yourself, as we try to describe about these two implementation strategies, strategy number 1 for sorted list, and also strategy number 2 for unsorted list, some of their operation scheme is similar to what we spoke about earlier about the sorting. One is about insertion sort, and the other one is about selection sort. I'll try to briefly remark about why you can draw such connection, but it's not exactly identical, don't get me wrong, but they do share some similarity for one of their subroutines for the algorithm to actually work. Right? That's something I'll remark in a moment. And we're just going to talk about a table for describing how you can implement the various public methods for the priority queue interface using a singly linked list. Let's talk about it. Right, so this will be the table that we want to go over eventually, but for now, let me set the context first. Approach number 1. Let's say we have a sorted singly linked list based on a key value. So that means the K1 over here is always the minimum key value. Right? So K1 over here is always the minimum key value. Meaning that it is the highest priority. Right? It will be very important, first of all, to really understand it. Minimum key, highest priority. On the other hand, symmetrically, what about the rightmost entry over here? So this will be, of course, the maximum key value, and accordingly is going to be the lowest priority. Right? That one is also very worth noting. What about any arbitrary neighboring entries? So let's say I have some entry over here, some entry over here. Let's say this one is at position I, this one is at position J. So what property can I actually assert between these two entries? Well, since it's going to be sorted based on the key values, so it's guaranteed. Let me just write it down over here. It is actually guaranteed if I try to compare these two entries over here, it is guaranteed that the Ki is actually less than or equal to Kj. What does it really mean when Ki is actually less than or equal to Kj? That means this particular entry is considered as more important than this entry over here, right? So this really means entry I somehow is more important, right? I'll just say more because it has higher priority. More important, which means it might actually get handled first. Then entry at index J. Right? It will be very important for you to also note this as well. Okay. Let me just use blue. Right? About this and also this. That's about a sorted list. And what about unsorted list? Well, for the unsorted list, well, literally speaking, right? So that means the list is simply not sorted in any way. We cannot assume anything about the first key, the last key, or any neighboring keys. You just cannot assume anything. It's just arbitrary, right? As easy as that. Given the context over here, let's think about if we want to use approach number 1 versus approach number 2 as the underlying implementation for the priority queue. How is it going to impact the running time for the priority queue operations? And remember, we got 1, 2, 3, 4, and 5. We got 5 different priority queue operations, and let's now talk about each one of them using strategy number 1 versus strategy number 2, right? So let me just make a quick notes over here. So this sorted list over here is definitely approach number 1. And unsorted list over here is definitely approach number 2, right? You can just draw this to this and draw this to this visual, okay? And for the size and it's empty. So these two should be rather trivial, right? They should be simply just constant running time, because in order for you to get the size for this singly linked list and to really check to see whether or not it's empty, you can assume you might have some attribute value size, which we spoke about earlier. So for these two, not surprisingly, it's simply just big O of 1. Okay, hopefully you're okay with that. And let's talk about, let's say, for the minimum. For approach number 1, how can I find out the most important entry? Well, as we suggest, we can simply just go to this particular one, right? This will be the most important entry to handle right away. In that way, we should simply go to the head of the list. So that's why it will just be big O of 1. What about the case of the unsorted list, as is indicated over here? Since it is unsorted, you have no other way but you have to search through the entire list, maybe from the beginning until the end, in the worst case, to find out which entry has the minimum key value. In that case, it's going to be big O of n, so linear, right? You can see it's a very important difference to see right away. Right? Let me just highlight it. In the case of the minimum over here, you can see the winner should be the sorted list, big O of 1. On the other hand, you can see for unsorted list, it's really the loser because it will take linear time, which is substantially more expensive than big O of 1 asymptotically. And let's talk about insert. But there is no silver bullet. So the approach being more expensive in one method may be cheaper for the other method. That's something you want to keep in mind as well. What about insert? If I want to insert into the sorted list, so this is similar to how we handle the sorting algorithm for insertion sort. So this is something I would like to make a quick note over here. Insert to the right spot. This is kind of the concept we spoke about in the insertion sort, so I don't need to repeat it. You can definitely refer to the insertion sort for more details to recall. Similar to insertion sort. Similar. Okay. And by the way, this part over here, searching for the minimum, is actually similar to the selection sort, right? Remember selection sort, we have to keep selecting the minimum. Similar to selection sort, which I forgot to remark, but I'm going to do it now. Okay. Right, so what will be the running time? If you want to insert a new entry into the priority queue, if the underlying implementation is a sorted list, you don't really want to break the sorting property for the list. What you're going to do is you want to find out exactly where to insert the new entry into the right spot, such that the new key is actually less than or equal to the next key, and also larger than or equal to the previous key. Right? That's something you will have to do. And how you implement it, it will be up to you. That's something we spoke about also in the earlier lecture. And that one there, in the worst case, you may have to go all the way to the end over here and find out maybe you have to put the new entry as the tail. That's just one example, worst case. In that case, it's going to be big O of n. As you can see, it's very expensive. Right? Over here, right? Big O of n. On the other hand, if I want to insert just for the unsorted list, if the unsorted list is the underlying implementation, in that case, it doesn't really matter. Because this list is unsorted anyway, I can just always insert maybe to the front or to the end. Doesn't really matter. Right? Well, of course, if you want to insert to the end, assuming that you got a tail reference, that'll be big O of 1 as well. Right? You can see this one here is definitely cheaper if you try to do the unsorted list. Okay, that's the one. You can see that for the minimum and for the insert, one can be more efficiently implemented by approach number 1, but the other one can be more efficiently implemented by approach number 2. So which approach you should really choose depends on you want to make your judgment about which one is actually going to occur, which operation for the priority queue is actually going to occur more often for your application. If the minimum is actually going to occur more, in that case, you definitely should really go for approach number 1. If you're going to do insertion more, in that case, you may have to go for the approach number 2. Right? That's kind of the judgment call you have to make. Okay. So let me just make one example. I would say, for example, if the application has more frequent calls to, let's say, minimum, in that case, you have to definitely choose approach 1, and etc. Right? Just one example about how you can make the judgment call. The final method we want to talk about will be removement. So this one here will be similar to the minimum over here, because in the case of the approach number 1, we know that the first entry is already the entry with the lowest key or the highest priority. In that case, we can simply remove the first In that case, it's going to be just constant, right? That's the basics about how to the running time for a singly linked list, big of 1. What about removement if the underlying implementation is an unsorted list? In that case, you definitely have to search for the minimum to find out which node it is and then remove that. But the worst case running time to search for this particular minimum entry to remove will be linear time, right? So that's why you will see linear over here. And of course, overall, you want to judge to see out of these 3 operations, which one will occur more often in your application, and then you will choose the approach accordingly. So later on in the assessment, make sure you're clear about this particular table in your mind. Well, of course, you can always recreate the structure from scratch by visualizing them, so you will be able to answer any judgment question posed to you. Alrighty, so that's about a very quick walkthrough about how you can implement a priority queue using list. Or linked list to be more precise. You can definitely do some exercise over here, which I'm gonna write down. Exercise. Okay, over here. Think about use a doubly linked list for approach number 1 and approach number 2. Does it make a difference? Running time wise. Does it make a difference to the running time? That's a question posed to you. And let me highlight it. And like here. And given this understanding about priority queue, its interface, and some preliminary, not so efficient implementation, we're going to see how we can improve the running time for the priority queue operation, specifically for insert and remove. We don't really want to get to the case where we got linear. We want to improve it. And we're going to cover a new data structure called a heap. Using a non-linear data structure, using a tree-like data structure, we will be able to improve the performance from linear down to logarithmic. That's something we'll see later in the next part.